All right, welcome back everyone to our fractional calculus seminar series. Today's speaker is Professor Tibor Pogany. He was born in Apatin, former Yugoslavia, in 1954. Education, elementary and high school in Hungarian, BSc Statistics and Applications major in 1978, MSc in 1981 and PhD in 1986, both theses in stochastic processes, all with the University of Belgrade, Faculty of Sciences, Department of Mathematics. Habilitation in 2015 in the Doctoral School of Applied Mathematics, Obuda University, Budapest, Hungary. He worked for 8 years in a high school teaching experience, 1978 to 1986, and 33 years teaching students in undergraduate, graduate, master and doctoral studies in STEM at the Faculty of Maritime Studies, University of Rijeka, Croatia, from 1988. Assistant Professor, 1987 to 91, Associate, 92 to 97, Professor, 1997 to 2002, Full Professor Permanent Position, 2002 to 2019, Professor Emeritus since 2020. In the Institute of Applied Mathematics, Grunwald Neumann Faculty of Informatics, Obuda University, Budapest, Hungary, as Research Professor 2013 to 17, and University Professor from 2017 onwards. Erdos number 3 in 4 ways. Mathematical Reviews entry record 202, Zentralblatt entry record 212, Editor-in-Chief of the Journal of Classical Analysis and editorial board member in another 5 to 6 journals. Research interests, special functions and their applications in statistics, Whittaker-Kotelnikov's Shannon sampling reconstruction of deterministic and stochastic signals, analytic inequalities. Still Serbian national club record holder for U17 in 4x400 meters relay, achieved September 13th, 1970. Yugoslav vice champion for U19 in 110-meter hurdles from 1973. So it is a great pleasure for us to hear from him today on the topic of the use of Grunwald Letnikov fractional derivative in analysis. Please, the floor is yours.
Thank you. First, I just switch to my slides. Can everyone see it?
Yes.
Okay, thank you. First of all, thank you very much inviting me to give a talk about that topic on use of Grunwald Letnikov FD. And I am really touched with that, seeing many old colleagues, friends, co-authors in the auditorium who just follow that my talk. First of all, why Grunwald Letnikov? The fractional derivative is coming in my interest area many years ago when I began to work and publish some papers with a late Indian mathematician Ram Kishore Saxena, and they just and I think he and his co-authors are very frequent in that area, but mainly using a Riemann-Liouville fractional derivative. Somehow it was novel to me to see that part of approach to solving problems, and I find that maybe the Grunwald Letnikov is very applicable in solving some strange and complicated integrals in which Laplace kernel is in there, because Grunwald Letnikov fractional derivative of Laplace kernel is almost the same that in the ordinary way when we want to derive the exponential function. So it was not too hard to switch to that approach, and somehow I implement in a few problems where it was necessary to solve some integrals. First of all, there are some incomplete integrals that are, for example, the incomplete gamma function, the lower and the upper incomplete gamma function. That means that when the integration interval is a positive real half-axis, then we just choose some point x between 0 and infinity, and the integration interval from 0 to x just give us the lower incomplete gamma function, and from x to infinity the upper incomplete gamma function. So incomplete Lipschitz-Hankel integral is nothing else than the Laplace transform, also in a finite interval from 0 to some x. And what is coming out? There we can solve that integrals, present them in form of higher transcendental functions like Exton's double hypergeometric function, and also Kampe de Feriet, many elements, many functions and series which belong to the hypergeometric family are there, and then are coming some functions defined by Laplace type integrals like the Toronto function, Markov function, Nuttall Q, Srivastava-Daust S function, and something like that. You will see which kind of hypergeometric functions are involved in that my talk. When we begin to speak about fractional calculus, that is almost in all cases connected with the Mittag-Leffler functions. However, I will not mention here neither the initial Mittag-Leffler function, Wyman function, Prabhakar function, and other multi-parameter and multivariable Mittag-Leffler functions, and the generalizations like Leroy type hypergeometric functions, which are present in very recent investigations by Professor Kiryakova or my co-author Jordan Kapaneva and Garapa and Gara, and also I think Tomovsky is here, and this time I am just reduce my talk to hypergeometric type functions. First of all, I just show you what is the what we need to define hypergeometric type functions. Then ILHI is just an abbreviation of incomplete Lipschitz-Hankel type integral. GLFD is a Grunwald Letnikov fractional derivative, and CDF is an abbreviation of cumulative distribution function, because of somehow I feel to be attracted to probabilistic background, since in my faculty days I finished the probability and applications major many years ago. So Fi is nothing else that a cumulative distribution function of CDF of a probability distribution connected to modified Bessel function of the first kind, and we express it with Exton's X function, Horn's functions, which are nothing else that phi2 is and also phi3, and that are some confluent hypergeometric functions of two variables from the Horn's list, which I remember 33 or 34 members contain. Also, Srivastava-Daust S function is, I think, one of the most general hypergeometric function of several variables, and generalize also the next 0.6, the Kampe de Feriet generalized hypergeometric function, and then are coming the Markov, Nuttall, and Toronto functions. The references list is exhaustive. I hope so. And first of all, I just have to present you which references contain the main results of my search. First of all, from 2021 to 2025, there are, I think, there are exactly 7 papers, and I have to mention too, but you can see that there are my co-authors also, Katarzyna Gorsk and Andrzej Horzela, and my most frequent co-author is my doctoral student, the Dragana Yankov-Marshirevich, and also my physician co-author, who is physician or physicist, I am not sure. He is a physicist, okay. Najib Laraki, who is working in Paris, and he is working in heat transfer, and he is in thermal science specialist. And he posed a problem which we also solve by Grunwald Letnikov derivative. Okay, and finally, here is also in 7, not only Dragana, but her PhD student Natasha Ujic, and we are working now also in some topic which is connected also to classical analysis, and that is nothing else that Lambert wave function. Okay, first of all, many years ago, in 32, McKay and a bit later, some other guys and probabilists or interested people defined some density function for a random variable xi, and that you can see here has 2 different forms. Normalization constant y0 is here. The Laplace kernel is also there. Then is also the Mellin kernel, x on the power nu. But 2 modified Bessel functions are present, I and q. The modified Bessel function of the first, and the k is nothing else than the modified Bessel of the second kind. So we have a random variable and have a probability density function. Now, the modified Bessel of the first kind attract us more, so we skip the modified Bessel of second kind. So we have a modified Bessel function distribution just for the modified Bessel of the first kind. So that is Bessel I low. McKay is the inventor. So we tell that is nothing else than McKay I Bessel probability distribution. In 73, McNulty just presented many different forms and characteristic functions and other probability density functions, and we just picked up this one, that is the display tree. And you can see that the main thing is the I nu, Bessel function, the exponential function, and the power, and the other multiplicative constant is here, which is normalization constant. You know that the integral from 0 to infinity of the density is equals to 1. Now, how looks like that density function? You can see for different news parameter values from -1/3 to 5. You have different shapes for that, and we will exploit our ideas thanking to that integral, which is on the next slide. It is labeled by the number 4. That is the CDF, or distribution function. And you can see that from 0 to x, the integration domain is finite. That means that Laplace transform is an incomplete integral, and up to the multiplicative constant, which can be just skip. The main job will be done to solving that integral here. Xi tilde McKay I nu is nothing else that notation for that distribution. Now, a short introduction about gamma, Pochhammer, incomplete gamma, and incomplete Pochhammer symbols. You can see it, but I think that everyone who is present are interested in that functions, so, and know what is about. So I just can go to the next slide. And we are now on the generalized Fox-Wright and hypergeometric functions. Because of Fox-Wright function is invented by gamma function, not by Pochhammer. We should skip that kind of definition sometimes, and normalizing the gamma functions in 5 with gamma of AL and BL in numerator and denominator. We just go to the classical definition of the hypergeometric function of Gauss. The convergence region depends on the P and Q, the number of parameters in the numerator and the denominator parts, and we just switch from generalized Fox-Wright to usual generalized hypergeometric function. You can see now that everything is defined with Pochhammer symbols, and we are very happy when we have Pochhammers and not gammas, because of actually that's the same. So there are well-known hypergeometric functions, and finally we are here meeting Gauss hypergeometric function, which is also presented like the Kummer's confluent hypergeometric function with Pochhammer symbols. So the next surprise is that Fox-Wright function can be also incomplete, that one of gamma functions in numerator part we replace with the lower incomplete gamma function, small gamma and big gamma. The small gamma just cuts the integration interval from 0 to x, and that is x is a new parameter in that definition. Now are coming horns confluent phi2 and phi3. They have two variables. It is a double series, and also in numerator in phi2 we have two different Pochhammer symbols, B and B prime or B dashed, and a confluent one, phi3, is just with one parameter alpha in numerator, and beta is below. And you can see that there are very nice functions. They are convergent for any bounded modulus x, modulus y, modulus z, modulus w for the phi3. Now is coming the Srivastava-Daust very exotic function, and here are also Pochhammer symbols, but now we are not reduced just for one parameter, but the linear combination of many parameters either in numerator and a denominator part. Finally, there are conditions for convergence inside some disks when the modulus of one variable is less than of radius, and the radius is also a very long and complicated expression, but we never work with something like that. We just skip that part because of that part is very technical. Now is coming Exton's hypergeometric X function, which is a kind of Srivastava-Daust function, but the number of parameters is here, in our cases, more limited with respect to Srivastava-Daust. And the third parameters in any that section are 1 and 1. What is the D1 and D2? There are some just linear combinations of the A, B, B prime, C, D, D prime upper and lower parameters of that X function. And when they are positive, everything is very nice and good. And so the Exton's hypergeometric X function converges absolutely for all complex X and Y, which is with limited modulus. What is happened when delta 1 and delta 2 equals 0 and are less than 0, you can see in the paper, which is now nearby 55 years old, written by Harry Mohan Srivastava and Marta Daust. And yeah, I just mentioned that when delta 1 and delta 2 are negative, the convergence is true only in the origin for both x and y. That is the formal series. The Kampe de Feriet hypergeometric function is also a special case of Srivastava-Daust function, and you can see now in Pochhammer symbols that there is an R plus S is one variable in, and then R and S are variables of the second and third row in the parameter part of the description of that function, and it is also belongs to Srivastava-Daust S function class. Now we are coming to Ilhi and GL. The Ilhi is an incomplete Lipschitz-Hankel integral of the first kind modified Bessel function, because in the first formula you can change E nu with some other suitable function, and you can see that it is nothing else than a Laplace transform or a Mellin transform. it depends on your taste or on your needs in considering some mathematical methods or problems or models. But z is a finite number. When z is infinity, we can easily find that just checking some formula collection, for example, by Prudnikov, Britschko, Marichev, or I don't know, Grachstein, Rijik, or something else, or Oberhettinger, or Erdélyi, and co-authors, and can find there what that Laplace or Merlin transform is. But when z is not infinity, we are in trouble. So we have to find some other way to expressing that. And then what is actually the Grunwald Letnikov fractional derivative? That is the limit of an infinite series when h is running to 0 from the right, and that limit, when it exists, we just call it GL fractional derivative. That are the left functions. I never heard before that. I just find that left and right functions, but when I read, it was clear why we just introduced that kind of approach to that. Also, I was not aware that there is a same result in the GL derivative, which were made 23 years ago by Kostadin Trenchevsky and Živorad Tomovsky, a paper in the so-called Mitrinović Journal in Belgrade Electrotechnical Faculty mathematical journal, and it was a real order, something like a real order derivative of an exponential function. And that is actually nothing else than a Grunwald Letnikov derivative. And now we are switching with that Grunwald Letnikov to the first problem. The first problem is summing up a Neumann series problem. The Neumann series is there is some coefficient and there is coming Bessel function, and the summation index is in the order of the Bessel function. You can see that n is now in the order of Bessel function of the second kind. How can we find what is that expression? And because of k nu is not a complicated, but a Bessel function, modified Bessel function of the second kind, which is not so easy to handle. The result is the following. That is the theorem 40. That is the paper of Najib Laraki and mine in integral transforms and special functions. And we find that SAB is nothing else that normalization constant, and then is coming Grunwald Letnikov with respect to the variable q, which is nothing else than a square plus b square divided by 4 of a product of two Bessel function, modified Bessel functions of zeroth order of first and second kind. The first one argument is minimum of a and b are the parameters which are the input parameters in the sum Neumann series SAB, and the maximum is in of that values in the second kind Bessel function K0. What is the proof? The proof I will just show a few moments of that. We have a k nu of z, and that McDonald function or Bessel function of the second kind, and that is the integral representation. We replace it into the S, and then we have to sum a Laplace transform formula by which we have two E nu and K nu, E0 K0 product, and V plus minus is a result which we get from some quadratic equation. That is nothing special. So different, we have to find from that integral EQ the GLFD, and then summing up everything, get SAB here in the slide on the 21, I think, yeah, 21. And that is a result of our theorem. Without that Grunwald Letnikov derivative of the order 1/2, it was almost impossible to find our final formula. The next use of Grunwald Letnikov happens, I think, 4 years ago, when my frequent co-author Sarali Snadaraja and myself just get to give a most condensed expression for the following integrals. Two integrals are now in charge, A and B. You can see what is here, xp, then e on the exponential expression of the power 2. And we have also a longer quadratic polynomial on some real power u in denominator. And similarly, but more complicated, is b. Now, we solved it and sent it to Mathematical Communications, and it was issued 4 years ago. The result is the following. When d mu, big D, not the mat BB in tech writing, Grunwald Letnikov, but just italic D, is a parabolic cylinder function, and P is greater than -1, then we have a following expression. It is a normalizing constant, then a limit when A is tending to 0 from the right, then is Grunwald Letnikov derivative with respect to parameter A of the order -u, and here is what is now inside. First, we have a polynomial, then have an exponential, and then a sum or a linear combination of two parabolic cylinder functions. It is really complicated, and I don't think so that it is less than or less complicated than the original integral. But numerical tools are there to find the value of that integral, but you can see that it is an integral for minus to plus infinity. Here, everything is finite, but the problem is something else. It is a complicated expression. So maybe you can take the second result. That is a proposition 2 in that paper. When we have a trichomy confluent hypergeometric function, which is a linear combination of two Kummer or confluent hypergeometric functions, and then A integral is a bit shorter, and we have here only the trichomy hypergeometric function inside the brackets, the squared brackets to which we have to find Grunwald Letnikov derivative. How can we get B? That is a similar expression, but now the problem is that we cannot handle that just double to the number of Grunwald Letnikov derivatives, and there is an infinite series. So actually, I don't know what is the less complicated, the original integral or that approach using Grunwald Letnikov derivatives. But there are some inbuilt subroutines and routines to find the value of fractional derivative. So maybe it is better. I have some response concerning that question. Now, I would show you some results which need the probability density functions and the cumulative distribution function. How can we present it when McKay Bessel I Bessel distribution is present in our investigations? So when we have a density, there is also an integral of density is the distribution function. But we can build from that distribution function other distribution functions. For example, when you have a distribution function f, lemma 1 show that h1 and h2, the integrals of the distribution function in that form also are distribution functions. Also, when fx is a distribution function, lemma 2 say that gx, which is fx minus f1 by x, or the x on minus 1, also is a distribution function when f0 is 0. Lemma 3 said, then we build an R2+ successive applications of integral operator introduced in lemma 1. You can get also a distribution function. And finally, lemma 4 say that when you have a stochastic subordination between some random variables, x and x plus y, you have a following inequality 16. Now, we are going to represent the Ilhi in terms on Grunwald Letnikov derivative. Now, using Exton's x function. That was why I introduced the Exton's x function at the beginning of my talk. You can see here that the integral is a Grunwald Letnikov with respect the Laplace parameter b of the order mu, and the x1000001 is the number of parameters in the input Exton function. Also, we can work without Grunwald Letnikov, but now on completely other condition we need, that mu plus nu should be in real part greater than -1. What is the proof? We will skip it. Then we can get here nothing else that inequality for the Grunwald Letnikov fractional derivative of the Exton's function, which we proved in Ilhi in the previous theorem. You can see that that integral is less than or equal from the uniform upper bound 2 on the nu, 1/2 of the order nu is the Pohammer symbol, and here is sorry, a binomial in the denominator. And because of we have this, we have just to combine that with the relation 17, and we get our inequality in theorem 21. Now, when we present the probability density, not the probability density, sorry, the cumulative distribution function in terms of Exton X, there are several theorems, and how we can get that is presented in the theorem 8. That is very similar to the earlier result, but now we can see that in all that formula, there is the Laplace kernel and also the Merlin kernel. Bound for Exton's X function, that is without Grunwald Letnikov, so I am nearing the time when I have to finish my talk. So we should concentrate only for Grunwald Letnikov in the following results. And here is one. That is the theorem 11. You can see that is almost the same that the earlier one theorem, which one I present you. Now, horn phi 2. Also, there are just uniform and functional upper and lower bounds for phi 2, that horn function. And we just get it in the following way. You know very well that the cumulative distribution function is between 0 and 1. So when we take that fi is expressed in terms of a special function, and we say that that is nothing else than a CDF, that is less than 1, and we get an upper bound for phi 2 or some other suitable function. Now, when we want to complicate the situation, then just build a H1 distribution function by the integral, which was presented by lemma 1, and then just repeat the procedure. That is less than or equal 1 and is greater than or equal to 0. So we can get some, for example, monotonicity bounds for H1, H2, and phi 2 and other special functions which are involved in solving that problem. You can see that there are some quotients, ratios of horn type phi 2 in theorem 16, and on the right hand side is a simple monomial x on 4 nu plus 2. That is very simple, and I don't know how can we prove that without that simple probabilistic approach to that. Finally, there are some results about monotonicity results by lemma 4 when we repeat the building phi h1 and h2 with that integrals, and the proof is very long. So what is with Turan-Pal? Turan-Pal is a co-author with Erdős in a few articles, and Turan just give a inequality for Laguerre polynomials, but we just take the idea to build it for Gaussian 2f1. Here is the result. So the Gaussian 2f1 squared is applicable to get a Turan type inequality, and it is bounded about three gamma functions, and f2f1s is just an abbreviation, so it is not placed to write for other matter. And here is another mean of the functions which was involved in the Hardy-Littlewood and Polya inequality book, and just repeat the procedure and get some other result for that. I will skip the results by Kampe, Feriet, and that. I just want to show you about my last paper written by Janko Maširevich and Ujic, what we do here. So we have a Nuttall function, which is also an integral. Here is in integrand Merlin kernel, but it is now Gaussian e on minus t square half. Okay, we can just transform it to get nothing else that Merlin Laplace transform. But what can we to do with that? How can we to find it? Then we have also a Toronto function. The Toronto function's name is interesting thing. Toronto function is because of the inventor is a guy, Hitley, who just introduced it because of communication theory problems and issues in 1943. But because of his working as an electrical engineer in Toronto, he said that it would be nice to tell that it is a Toronto function. So that is TB is nothing else than the Toronto function. You can see what is the definition of that integral. And Mn are integers, and R is not an integer in that integral definition. So also there is an expression, how can we simplify Toronto functions? It is the Kummer function minus a Nuttall function. That is the connection between that. Now we succeeded to find what is some fractional derivative form of the Toronto function. That is theorem 23. That theorem TB-MNR is a Toronto function. You can see that it is a Grunwald Letnikov derivative with respect the parameter S of a Kampe de Feriet function, and S is present in the first variable S big square. And finally, when we find that Grunwald Letnikov, just put inside S equals to 1. And what is now the problem? The problem is that actually nobody knew what is a closed form of the Nuttall function, and we find that we can express it as a linear combination of a Kummer function, and here in theorem 23 also, but a bit later as a corollary for one in that paper of Grunwald Letnikov was the final step in getting something else than just a numerical integration and approximation of that integral. Here is an exhaustive list. I think about 50 different papers are there. I think that the main papers are here, and sorry if I haven't enough time, but I never thought that I can give a so long talk. Thank you very much for your patience.
Thank you very much for the talk. Do we have any questions from the audience? You can raise your hand or you can simply unmute and ask. I have one question. It's a sort of kind of heuristic question instead of something specific. With these special functions, you have a lot of series formulae and a lot of integral formulae.
Yeah.
Which one do you prefer or do you think is easier to deal with?
Okay, that is some question. Do you like more cakes or other cakes? I don't know, but I think that I prefer the integrals.
Hmm.
Why? Because of they are shorter somehow. You know, my good friend Tamás Mori from Budapest said always, no, I like the discrete probability. He's one of the famous probabilists from the Hungarian probability school. And I'm asked why. And he said, because of I haven't think about continuity. So when you have some function, you have to know what is the domain. It is convergent. Where are the singularities? I don't know, and something like that. When you have some discrete probability model, he said that everything is clear, and I have to. I have just have to work with that. I don't know. I like somehow better and prefer an integral.
Hmm.
So in I don't know about 15 years ago, I worked with Neumann series, Dini series, Schlömel series, Kaptein series, and series of Bessel functions, and just find with my co-authors and or just myself uh, the integral representation of that series. That is completely classical analysis. So I think that maybe I was born too late for that because of the great classical analysis workers, preferably in France or in Germany, Gegenbauer and Neumann and I don't know Bessel and uh, they work and lived in 19th century and in 20th at the beginning of 20th, and I just followed that way. So it was my occupation to find how can represent series in form of integral.
Hmm.
When you just want to build some upper bound, just have to, for integral, to use the modulus of integral and go inside and bound the integrand. And there have to, maybe it is complicated to explain, but that is that.
Hmm. Yeah, it makes sense. At least when you are working with both, you see the advantages and disadvantages. For me personally, I prefer series because I find
Oh, I
the
see.
convergence of series is easier to prove. You just look for the radius of convergence and that's it. Whereas with integrals, it might be more
Definitely.
complicated.
I agree. Yeah. Yeah.
Thank you. Any other questions from anyone else? All right, then I will stop the recording here. Thank you very much for the talk.